Alright, Electronics 1, Resistor and Network Analysis. Eugene E. Mikoval, College of William and Mary, January 25th, 2010, Week 1. Analog electric circuit goals. Major time spending experimental preparation go to design construction interface different electronic components, often commercial circuitry, not available or has to be matched with electronic front end responsibility. Those were collecting usually weak signals back end, which do general processing to perform above tasks we need. Lear basic discrete components, resistor, capacitor, inductors, diode, photodiodes, transistors, field effective transistors, operational amplifiers, commutators, multimeter oscilloscopes, function generators, breadboards and soldering irons, modern circuit design layout software, master their usage. As a result, we will be capable yet simple yet capable electronic circuits. Okay, resistors in a schematic on the board layout. So everywhere you see a zigzag line is a resistor, 2 lines capacitor. This would be an amplifier. This would be a jumper, ground, to another amplifier, to a resistors over here on this 3-way switch. With over here would be the board design. Instructor Eugene E. Mikoval, Office Millington, 251 Lab 7022, phone number 221-3571, Office. Email eemikh at wm.edu, website physicswm.edu, evicmic. Office hours 1415 hours. Alright. Your final grade of the course will be determined by the following grading: weight distribution, notebook, labs, lab reports, quiz participation, midterm, and we're not that. Midterms, lab books. Your lab book is primary record of work data, what you did, how you did it, how you made measurements, test equipment, how they were conducted, data, information enough to tell us data, what you observed, calculation analysis, including scratch work, plots, answer to questions, justification for your answers, diagram, data, photographs, other notes. Separate pieces of paper should be glued, taped, stapled into the lab book, and something fails out of the lab book during reading or shaking transport is not part of the lab book and will be discarded. The lab book will grade primarily on the completeness and lesser extent necessary. Lab report should be present when you did the lab, some of the aspects of what you did, along with encompasses the main theme of the lab. The report should have the following characteristics: components type, printed short report, max 3 pages. Structure, introduction, main body, conclusion, measurement, include with the table of plots. All data analyzed, interpreted, and measured numbers should include justice to error bar figures, label the number referred to in text. Lab books are due. Alright, Alright, basic blocks. We have short electrical potential difference, potential divided by volt, volt over electric over Quincy, derived with joules and calculus, system in SI unit of volt, current rate. Rate of flow of electric charge is D over Q over D over T, or ampere. A is equal to ampere, W is equal to watt. Energy, dE, time, and electric power is equal to voltage times the amperes, watt. Electrical resistance, R. Different objects have a different current passing through them with the same voltage difference applied, but it indicates have a different electricity, and that's the ohm signal. Amps equal volt over resistance. Standard lead is half watt, 1 watt, 2 watt, 2 watt. Power, surface mounted image. Here's a chart on resistors. Unloaded voltage divider goes to voltage 1, resistor 1 to voltage output, resistor 2. Voltage output is equal to voltage input over resistor 2 over Alright, voltage output is equal to voltage input times resistor 2 over resistor 1 plus resistor 2. Alright, Chapter 1 Lab Manual. Alright, Chapter 1 DC Circuits Basics. Chapter 1 DC Circuits Basics. Overview electrical circuits depends on the first and foremost understanding simple basic quantities used to describe electricity, voltage, current, power. The simplest circuits are related to Ohm laws. After defining and understanding these quantities, we'll discuss the discussion network and also let a few examples. Voltage, measured in volts or V, is measured between 2 points in a circuit. It is the amount of the potential energy delivered per unit charge as the charge flows along the circuit. You measure the voltage connecting two terminals of the voltmeter to the 2 points in the circuit. You must measure the voltage while the circuit is operating. If you have a good voltmeter, the measured voltmeter is the same with the voltage was before with connecting the voltmeter. Voltage decrease with the direction of the current flow represents the energy flowing out of the circuit, usually into heat. Voltage sources such as batteries, power supplies, producing voltage along the direction of current. Current measured in amperes or amps or A, which is equivalent to coulombs a second, with the measure of the single point in the circuit with the rate of the charge or flow along the circuit with the measure of the current. And with a current meter or ammeter, you must break the circuit at a point and connect end with one of the terminals in an ammeter circuit. It can only flow with a complete circuit. If this is switch stops with the electrical circuit, it breaks the circuit and interrupts the current flow. Power. Power is measured in watts, the rate of electrical energy converted into heat, some of the other form, and energy, also known as the energy conserved with the circuit that needs power and supply or battery that converts the energy into electrical energy in order for it to operate. Power consumed with the production of the current flowing from the element at times of the voltage drops off. The power is equal to amperes times the volts. P is the power, I is the current, V is the voltage. Alright, 4, IV, or 4 characteristics completely characterize any element with two terminals as 4 characteristics. How does it make currents through it, given the voltage across of it? 4 characteristics given with the function I and V or I is frequently defined graphically. Ground. A ground is the name with a given to the voltage. The zero reference point makes it easier to refer to the voltage, so you generally assume that second point of the ground, if not explicitly stated, will also represent the implied completion of the circuit, even when we do not explicitly show the wire connection presenting a different place in the circuit. Since all ground connections are connected together, resistance. A resistor is a two-terminal device converts voltage into a current and converts a current into a voltage. The current through the resistor always relieves with the voltage dropping off the resistor, or Ohm's law. Voltage equal to amps times resistance. The resistance is measured in ohms. Also means that the resistor generates heat with the current flow given as the power is equal to amps times volts equal to amp squared times resistance equal to volts squared over resistance. Each expression given an answer to be but one another will either depending on what you know of the circuits 1 or 5 or both. May seem simple to devise with just turning the energy into heat, but resistors actually perform an important role. They turn electrical energy into heat that can be used to make the electrical heater more likely to light a bulb. The light is just a form of the heat given off by a very hot source. Sometimes you dissipate power somewhere. For example, if you want to deliver 100 milliampere current to 12 volts to a part of your circuit, but your power supply only gives you 15 volts, then the extra power must go somewhere to dissipate the resistors rather than heating your sensitive transistors. If you have a voltage source and you want a specific amount of current, then a resistor does the job. It converts the voltage difference between the 2 points into a current flowing through the resistor. Sometimes we'll add a resistor in series in the circuit to prevent power supply from delivering too much current. In the case of short output lines together, this is called current limiting resistors. If you have a current flowing you want to convert so voltage, then resistor again solution that might seems a little more far-fetched because of the may not be familiar with the constant current sources. When beginning studies of transistor, we'll find that we behave as current sources. So you will use resistor and output to convert the current into the voltage. We consider capacitors, and week 3 will generalize resistance to AC circuits along with a phase shift that we will call the generalization complex plane. Impedance for this week, we'll assume the resistance and impedance instead of being the same. Network analysis. If you connect one power supply, lots of resistors together completed with a network of the currents of the flow through the various elements to ensure that the charge is conserved Energy is conserved by the Ohm's in itself. Ohm's law is satisfied, simultaneously satisfying all the conditions, giving you exactly one solution. The sure, but the two resistors proceed with a more complicated system. Specifically, two resistors in series will draw the same current equivalent resistors of the resistance. This is stated mathematically as resistance. Resistance saturated is equal to resistor 1 plus resistor 2. Ultimately, two resistors are resistor series equal to resistor 1 plus resistor 2. Two resistors parallel draw equivalent resistor with a resistance. One resistor in parallel is equal to one resistance, 1 over the resistor 1 plus 1 over the resistor 2. A resistor parallel is equal to resistor 1 times resistor 2 over resistor 1 plus resistor 2. Note that the resistance 2 resistors are parallel always if they're smaller but not less than half the small resistance. If two resistors differ in large factor, they can ignore the larger resistor. For example, the 1 kilo ohm is parallel to 1 mega ohm is within 99 mega ohms or very close to 1 kilo ohm. Standard resistors come very different ratings more than this lab, so in general you get in any particular volt value you want. One can make up with equivalent resistor few resistor series parallel combinations to get much larger range for the options. The design exercise 1 have the design network to have the specific resistance given a very limited series resistance. Voltage dividers. By far the most useful thing you can do is with two resistors to make a voltage divider, which just as two resistors in series with voltage dividers are shown schematically. Figure 1 on the right, two slightly different but equivalent representations. It divides the total voltage into two parts, in which each part proportionally to the resistance in the leg. So if you know the starting voltage and the target voltage, then calculate the required ratio of two resistors. Voltage output is equal to voltage input over the resistor 2 over resistor 1 plus resistor 2. Design exercise 1, you get to derive this relationship. Figure 1.1 shows two alternative schematics for a same voltage divider. Alright, a load voltage divider. Of course, you will see that the voltage out of the voltage divider is connected to something, usually another resistor, figure 2, but then the change with equivalent resistance lower leg, will therefore change with the voltage across the leg. In order to the actual resistor values you have with the two competing sources, low resistance makes of the divider less sensitive to loading. When you get the target voltage, too high resistance draws less current, therefore use less power. When spending more of the time on the formalized the consideration coming weeks. For now, let's just consider what happened to the voltage divider when we connect to the load resistance RL from its output over the ground. In this case, to replace the resistor 2 from expression unloaded divider of the equivalent resistor 2 in row resistance, load resistance, and parallel to this give the voltage across resistance 1. Voltage out and loaded equal voltage input over the resistor 2 parallel with the load over resistor 1 over resistor 2 parallel to the load or voltage, and then when resistor 2 is parallel with the load, equivalent resistor 2 and resistor load are parallel resistor 1 and parallel with resistor 2, equivalent resistance resistor 1, resistance over the resistor 1 and 2, parallel voltage unloaded, output voltage unloaded with the voltage divider. Last expression, clearly loaded voltage is always less than the unloaded voltage, smaller load, larger. Difference between the load and the unloaded load resistors do not affect the output significantly, so if you want to ensure that you do not affect the output of the device, you would likely have the input of the device to look like a large resistor and output look in the case of the resistor 1 parallel to the 2 looks like a small resistance. Next week we show that there is a general conclusion more formally defined in the concept. Design exercises. Chapter 1, DC Circuit Basics. Alright, your lab voltage. We're going to skip the labs. We'll just pretty much do the slides then.